We used to think of science as a peaceful activity. When we say this word, we think of endless corridors, snow-white laboratories, and people in awe-inspiring silence working on devices so complex that it is almost impossible for an ordinary person to understand their tasks. But is it really so? Has it ever happened that in the scientific world broke out real wars? Of course. In fact, what I will tell you today can horrify even the most inveterate skeptics, and the universe which you imagined will seem completely different.
Affairs in outer space.
The concept of quantum jump is one of the fundamental concepts of quantum mechanics. It is a very popular term which came into use largely thanks to the sci-fi series of the same name, released in the early 90s. But do you know what this concept actually means? A quantum jump is an instantaneous transition of a quantum system, for example, an atom, from one energy level to another. In other words, quantum jump theory implies that electrons in atoms jump randomly, moving instantaneously from one orbit or energy level to another, never occupying an intermediate space. It all began in 1913, when the great Danish physicist Niels Bohr investigated emission spectra, the sharp bands of color produced when electricity is applied to a simple gas tube. He built on the recent success of Max Planck, who in 1901 had investigated the radiation of a completely black body by suggesting that light was composed of peculiar beams of energy that were later called photons. The result was Bohr's model of the atom, based on Rutherford's planetary model. Bohr put forward the theory that electrons in atoms move along strictly defined orbits without releasing energy, and that emission or absorption can only occur at the moment of transition from one orbit to another, which is a quantum jump. Bohr's work inspired Werner Heisenberg and Erwin Schrödinger to develop the first complete formulations of quantum mechanics in 1925. Eventually, they were able to successfully predict the spectra of elements of any complexity, and much more. But one thing remained a mystery. What actually happens during a quantum jump, and what determined when it should happen in the first place? To address such questions, Bohr and Heisenberg teamed up to develop the Copenhagen interpretation of quantum mechanics. This interpretation describes transitions in quantum states as fundamentally random. Roll a die, and the system changes instantaneously. An electron moves from one energy level to another without moving between them. Then there was also the view that measurement destroys the wave function. In other words, interaction with the environment causes a transition from one state to another. That is, it causes a quantum jump. But one person was not impressed with this idea. Who do you think? The inventor of the wave function himself, Erwin Schrödinger. When Bohr visited his home in 1926, Schrödinger said, "If we still have to put up with these damned quantum jumps, I regret that I ever had anything to do with quantum theory." In 1952, Schrödinger published a two-part essay titled, "Do Quantum Leaps Exist?" In it, he compared the theory of quantum jumps to the theory of epicycles, a long-dead theory of the motion of planets in the solar system, centered on the center of the Earth. He argued that both epicycles and quantum jumps were ingenious constructions of the human mind that were nevertheless not true descriptions of nature. So why did Schrödinger hate quantum jumps so much? Simply put, they seemed unnatural and unphysical to him, hiding a phenomenon that quantum theory could not yet properly explain. The debate about quantum jumps was only part of a larger discussion about the quantum nature of reality. Albert Einstein also opposed the notion, saying, "God does not play dice with nature." Albert Einstein. This was his reaction to the view that subatomic phenomena are fundamentally random or probabilistic. But Schrödinger had his own arguments too. He believed that everything comes down to waves, and that there was nothing special about these waves compared to any other kind of classical wave. He argued that most strange quantum phenomena could be explained by classical resonance phenomena. He rejected the idea of the photon as an irreducible energy packet, and even the idea that electrons transition between discrete energy levels. He argued that the same radiation spectra could be obtained by treating these levels as some kind of fundamental oscillation, as with a drum or guitar string. Then the atomic electron could be viewed as a superposition of several vibrations. And this meant that the electron could move smoothly through a number of intermediate states during each transition, rather than undergoing instantaneous quantum jumps. For Schrodinger, a large part of the problem was that Bohr and others used the behavior of systems of many particles to infer the behavior of individual units. He believed that it made absolutely no sense at all to even think about individual particles. As he put it, we never experiment with just one electron or atom. In mental experiments, we sometimes assume that we do. This invariably has ridiculous consequences. That was in 1952, and in 1952, we had never seen a single photon produced by a single quantum jump in a single atom. But times are changing, and science is discovering things that were not even imaginable before. Proving the theory of quantum jumps required precise measurements that didn't exist in Schrodinger's time. Yet they exist now. Has the reality of quantum jumping finally been proven? By the 1980s, mankind had learned how to trap and cool a single atom using lasers. And in 1986, almost simultaneously, 3 different teams of scientists managed to capture quantum jumps in such a separated atom. How does it work? The essence of the experiment was that the atom bathed in a laser beam of a certain frequency, finely tuned to the energy difference between its 2 electronic levels. The electron, moving conditionally from the first level to the second, absorbed a photon of laser radiation, and returning back from the second to the first, emitted an identical photon in a random direction. That is, emitted some fluorescence. For the correct choice of energy levels, this must happen extremely quickly. The electron must be trapped between the 2 levels. In experiments in 1986, the electron in the trapped atom jumped between levels about 100 million times per second. When the electron was on the more stable 3rd level, it went out and disintegrated because it could not return to the closed system of the 1st and 2nd levels. So physicists were able to get fairly direct evidence of quantum leaps, and the jumps down, when the electron decayed from level 3, apparently occurred at completely random moments in time, just as Bohr had predicted. So that settled the matter. Schrodinger was wrong, and Bohr was right. Right? Not so fast. Although the jump seemed random, there was no way to tell if it was instantaneous or if the electron went through some intermediate states during the jump. Technology has now advanced to the point where we can not only see individual quantum jumps, we can follow their progress and even interrupt them mid-jump. Scientists conducted an experiment with an atom that can be called an artificial atom, consisting of 3 different energy levels that corresponded to the number of electromagnetic quanta of energy stored in the circuits. The researchers placed these artificial atoms in a microwave resonator, an analog of a laser, which could make the atom go from one state to another. This also allowed the researchers to monitor the state of the system with much greater resolution than in the 1986 experiment. The scientists were able to zoom in on the quantum leap and finally find out if it was indeed an instantaneous transition. They found that no. After all, it was not an instantaneous transition, but rather a continuous transition through intermediate states that took several microseconds. And this transition seemed to be perfectly described by theory, in this case, quantum trajectory theory. But what about the randomness of the event? Well, the interval between events did turn out to be random, just as Bohr had thought. But just before each jump, the system began to shift in such a way that the researchers could predict the approaching jump. And this ability to predict also allowed them to reverse quantum jumps in flight by adjusting the microwave field during the process. Given that the onset of the quantum jump was predictable and that its trajectory was extremely well described by theoretical calculations, one is tempted to wonder if the whole process is a deterministic mechanism rather than a fundamental randomness. What is really going on here? Some time ago, a group of theorists claimed to have taken an important step toward clarifying this phenomenon. They explained this non-instantaneous quantum transition in terms of the so-called quantum Zeno effect. The theorists have shown how quantum states can transition very predictably through a series of superposition states, much in the way Schrodinger proposed. But in addition to these predictable quantum jumps, there are fundamentally unpredictable, really unpredictable and sudden quantum jumps that would have made Bohr feel like a winner in an argument. What's the difference? This is related to how strongly the system is coupled to the measurement instrument. The weaker the measurement, the less probability of a true quantum jump. It turns out that at this point, the Bohr and Schrodinger camps have new evidence in their favor. For a long time, physicists have avoided asking which interpretation of quantum mechanics is correct. Many thought it was a matter of philosophical preference, whether you roll the dice with Bohr and Heisenberg, or ride the continuous and deterministic wave of Schrodinger and others. But the experimenters turned out to be much smarter than the skeptics assumed. Nearly a century after Bohr and Schrodinger started this argument, we may be on the cusp of the next quantum leap. To the study of whether quantum jumps are instantaneous or continuous, and perhaps even whether the quantum world is built on fundamentally random processes or governed by rigidly deterministic space-time mechanics. Science is not standing still on this issue, and our channel is sure to highlight the evolution of the resolution of this old scientific controversy. And you can help us in this. Do not forget to put a like and subscribe to Hubble. With us, you will always be aware of what is happening in modern basic science. And as usual, if this video gets exactly 25,000 big electronic likes, I'll release a new video that will keep your mind active for days to come. Remember, to give a like, all you have to do is go below this video and click on the thumbs up that looks like this.